Imagine you tell your brand new AI assistant to run a simple database cleanup. You type, delete all inactive customers. On the surface, the intent is clear. Many developers start by building this, a direct connection between the AI agent and the production database. In this setup, there are no filters or checkpoints. The AI has the keys to the kingdom. But large language models are probabilistic. They don't always interpret context the way we do. In this case, the AI decides inactive means any customer who hasn't logged in for 90 days. It creates a massive deletion command and fires it off instantly. 2 million customer records vanish. Because the AI had direct access, there was no confirmation and no undo button. By the time you see the error, the data is gone. AI offers incredible speed, but that speed is a liability when the system isn't 100% accurate. In high-stakes environments, letting a probabilistic model run high-risk tasks autonomously is a massive gamble. The problem isn't the AI's intelligence. It's the lack of a buffer between a brain that works on probabilities and a database that demands exactness. Let's reset the scenario. We issue the same command, but this time we've installed a physical safety barrier. Now, a middleman, the MCP server, sits between the AI and the database. The AI loses direct authority. When it attempts that 2 million record deletion, the request is intercepted. The system enters a pending state. The command is locked, unable to proceed without a green light. By routing every action through this protocol, we take away the AI's autonomy. It is no longer the final decision maker. It is simply submitting a proposal that requires a signature to move forward. To get that signature, the MCP server sends out a webhook, a digital notification that alerts a human supervisor that an agent is waiting for a decision. This alert translates the AI's technical intent into plain English. The human can see exactly what the agent wants to do, which records its targeting and the potential consequences of the action. The supervisor opens an approval dashboard. They have 3 clear options. They can approve the request, kill it entirely, or modify the parameters. The supervisor sees the 90-day deletion rule and realizes it's too aggressive. They click Edit, change the rule to target accounts older than 5 years, and hit Approve. The MCP server receives the human's corrected command. The data packet clears the checkpoint and updates the database safely. This shifts the human's role. Instead of spending hours manually cleaning data, you are acting as an editor, reviewing the AI's work and providing the final level of judgment. This pattern of request and approve is the same logic needed to secure other critical operations. Whether it's a bank verifying a large transfer, a cloud engineer shutting down a server, or a hospital updating a patient's record, the principle is the same. The higher the stakes, the more vital the human checkpoint. Because every action flows through the MCP, the system creates a permanent record of who approved what and when. This creates a clear trail for security audits, ensuring no action is ever hidden. Asking for permission does add a moment of delay, but a few seconds of human review is much cheaper than the weeks of recovery required after a massive data loss. Most companies will likely automate the low-risk, everyday tasks entirely, while keeping this manual approval layer strictly for actions that are difficult to reverse. Today's AI agents are like talented but inexperienced interns. They need guidance to be effective. Human-in-the-loop provides the bridge needed to make these systems reliable enough for the work we depend on every day.